this differential equation of the form some stuff with t's times y plus some more stuff with t's, what kind of equation is that called? Linear. Yeah. Okay, and when b of t is 0, that's a special kind of linear equation called? Sure. Yeah, you can call it unforced or homogeneous. Yeah. And when b of t is not 0, forced or non-homogeneous. All right, so give yourself a score on your folder. Okay, so thus far we've only learned one analytic technique for finding solutions to differential equations, that's separation of variables. The technique is very limited because it only applies to a very special kind of differential equation. But we have studied some qualitative and numeric techniques with slope fields and Euler's method, and they can be applied to a much wider variety of equations. But the problem of finding analytic solutions is tough because the existence theorem very frequently guarantees us that a solution exists, but there's no guarantee that that solution is a simple function made up of the elementary trig, exponential, polynomial types of functions that we know. And in fact, usually they're not. Okay. So there is no general approach to solving a differential equation analytically. Differential equations have been studied for about 300 years, and mathematicians have developed many solution techniques that apply to only specific classes of differential equations. And our course will cover a handful of them. And today we're going to develop one of the standard techniques for solving linear differential equations. And a first order differential equation is called linear if it can be written as some stuff with t's times y plus some more stuff with t's. Okay, so in other words, the differential equation is linear if it's linear in y. It's linear in the dependent variable. You can have squareds and square roots and trig things with t's, but not with the y. All right, so which of these equations is linear? Yep, this one's linear because it's y to the first, right? How about the one below it? Yep, we have a y to the first. Doesn't really matter what t does as long as we just have a y to the first. How about this one here? Yeah, it's linear in the y's. And this one, yeah. How about the right? Nope, because it's y squared. How about this one? Yeah, p is the dependent variable. It's p to the first, so yep, that's linear. W to the first, yep. Right. Z is the dependent variable, and we have sine of z, which is not linear. So linear differential equations come in two flavors. If b of t is 0 for all t, then the equation is homogeneous or unforced. Otherwise, it's non-homogeneous or forced. So let's label these as either homogeneous or non-homogeneous. This first one is homogeneous, yep, because there's no other term. There's an a of t times y, b of t is 0. Oops. Okay. And then how about the second one? That's non-homogeneous. Your a of t is just the coefficient of 1 in front of the y, and your b of t is your sine of 2t. Okay, every non-homogeneous linear equation has an associated homogeneous linear equation where you just drop the b of t. Okay. So for the one in number 6, it's associated homogeneous equation. We're just going to drop the sine of 2. Oops. Just drop the sign of 2t, so the associated homogeneous equation would be dy dt equals y. So we have a 3-step procedure for solving linear differential equations. Read your text for why this works. We're just going to practice it for today. So the first step is find the general solution of the associated homogeneous equation. This you'll be able to do with separation of variables, right? Because it's linear, you should always be able, once you drop the b of t, you should be able to do this. So you just use separation of variables. Then step 2, this is the hardest step. Find one particular solution to the non-homogeneous equation. You have to be able to sort of come up with one solution, not the general one, because that's what we're working on, but one particular solution, any function that makes the non-homogeneous differential equation true. And then to get the general solution of the non-homogeneous equation, add your results from 1 and 2. So step 2 is the hard part, and we usually find our particular solution by making a smart guess. And it really just comes down to guessing, and often you'll guess wrong, and you just try again. All right, so let's just verify that the procedure works for a sample linear differential equation. And for demonstration purposes, I'm going to give you the particular solution this time. And then in the next one, we'll practice guessing. Okay, so step 1, find the general solution to the associated homogeneous equation using separation of variables. So we just drop the b of t, and we're trying to solve dy dt equals cosine of t times y. So I want all the y's on one side, t's on the other. So this becomes 1 over y dy equals cosine of t dt. And then you integrate both sides. The integral of 1 over y is ln y. The antiderivative of cosine t is sine of t. And I'm going to put my constant of integration just on the right. And then how do I get the y by itself? Raise e to both sides. Yep, e to both sides. So e to the ln of y is y. And then I have e to the sine of t plus c. But then there was that fancy little trick that we use a lot, right? That we can actually rewrite this as e to the sine of t times e to the c. Because when you multiply like bases, you would add the exponents. So we're using that rule backwards. And then e to the c is just another arbitrary constant. So this becomes y equals, we'll call it k e to the sine t. So that is just step 1. That's the solution to the associated homogeneous equation. Step 2 is to come up with a particular solution to the whole equation without dropping the b of t. So normally we'd have to guess at it. I'm just going to have you confirm that t over 5 is a particular solution. So I'm going to write down the differential equation again, cosine of t times y. Plus 1/5 1 minus t cosine t. Okay, so my potential solution is y of t equals 1/5 t, t over 5 and 1/5 t, same thing, right? So if y of t is 1/5 t, what's dy dt have to be? 1/5. Okay, so I'm going to take these two pieces of information, one I gave you and the other I just took the derivative, plug both of those into the original differential equation and see if the left side equals the right side. That's how we check that a solution is true. So dy dt I replace with 1/5. And then we want to see, does that equal the right-hand side when I replace all my y's with 1/5 t's? So just leave cosine t as it is. Replace the y with 1/5 t plus 1/5 times 1 minus t cosine t. Just plugging in the solution. If the left equals the right, then it really is a solution. Okay, so 1/5. Does that equal? So I have 1/5 t cosine t plus 1/5 minus 1/5 t cosine t. Just distributed that 1/5. I have these two terms that cancel, and I get 1/5 equals 1/5. So I know that t over 5 is a particular solution to the non-homogeneous differential equation. So I have two pieces of information. I have the general solution to the associated homogeneous equation, and I have one solution, one particular solution, which we all often denote y sub p for y particular, to the non-homogeneous differential equation. People still working on this algebra? We're good? Okay. All right, so step 3 is the general solution to the non-homogeneous differential equation. You can get that by adding the general solution to part 1 to the particular solution we just confirmed in part 2. So I often write y sub g for y general. That is, what was my general solution? It was k e to the sine t, and then my particular solution is t over 5. So k e to the sine t plus t over 5. And then I want to confirm that that satisfies the non-homogeneous differential equation. So if y is k e to the sine t plus t over 5, let's look at dy dt. What's the derivative of that? So the derivative of k e to the sine t would be k e to the sine t times cosine t, chain rule, right? And then plus the derivative of t over 5 is 1/5. So I want to confirm that this is a solution to the differential equation. So I'm going to rewrite the differential equation, plug in y and dy dt, and show that the left side equals the right side. All right, so dy dt equals cosine t times y plus 1/5 1 minus t cosine t. Okay, so I replace dy dt with k e to the sine t times cosine t plus 1/5. And then does that equal the right-hand side when you replace y with the general solution? So I have cosine t times y, which is k e to the sine t plus t over 5. All right, so when I simplify this, I should see that the left side equals the right side. And the left side is as simplified as it's going to get. I'm going to work on the right side, do some distributing, probably combining like terms or canceling, and we'll see what we get. So distribute the cosine t, and I get k e to the sine, oops, k e to the sine t cosine t plus 1 plus t over 5 cosine t plus 1/5 minus 1/5 t cosine t. So t over 5 cosine t minus 1/5 t cosine t, those cancel. And does the left side equal the right side? Yeah. Both sides are k e to the sine t cosine t plus 1/5. Yeah, so it worked. We found the general solution. Yeah. So this was the answer. This is the general solution to the differential equation. Okay. And we were checking it. Yeah. One of the ones, this, that's a t. Yeah, t over 5 cosine t. So we have a general solution. Let's confirm that this is the general solution by looking at the slope field. So I created a slope field with a computer, and you can see that our particular solution, t over 5, is a very special solution. It's a straight line. And that is the particular solution that corresponds to k being 0. Right? And then we have other solutions for different k's. Right? So I have when k is 3, when k is -2, and when k is 1. And you can see that those curves perfectly follow the slope field. They do appear to be solutions. Okay, so the guessing step. That's the hard step. I just gave you the particular solution this time. Let's do another example where we actually guess. So step 1, find the solution to the associated homogeneous equation using separation of variables. So this is dy dt equals -2y. It's the associated homogeneous equation. Get the y's on one side. 1 over y dy equals -2 dt. Integrate both sides. ln y equals -2t plus c. So skipping a few steps here, I get y equals k e to the -2t. All right, step 2 is our guessing step. I want to find one solution to the non-homogeneous equation, any function that makes the non-homogeneous differential equation true. So I'm going to rewrite the differential equation here. dy dt equals -2y plus e to the t. All right, so I'm going to do one simple thing that's going to make it easier for us to guess. I'm going to add the 2y to both sides. So dy dt plus 2y equals e to the t. So now just think about what the symbols mean. Dy dt means a derivative. So we're looking for a function whose derivative plus twice itself equals e to the t. So it has to be that the function and its derivative must be like terms. The function itself and its derivative would have to be like terms so that when I add them, I get an e to the t. So what kind of function and its derivative would be like terms? An exponential, yeah. So I'm going to guess that my y particular has the form alpha e to the t. It's some constant multiple of e to the t. Okay. And then I'm going to use that guess to try to figure out what the alpha is to make this work. So go back to my differential equation. So if y particular is alpha e to the t, what is dy dt? Y particular, yeah. What's the derivative of alpha e to the t? Alpha e to the t. Okay. So now I'm going to take these guys, plug them into the original differential equation, and figure out what alpha is to make this true. So dy dt is alpha e to the t plus 2 times y, which is alpha e to the t, equals e to the t. So I have alpha e to the t plus 2 alpha e to the t. That's 3 alpha e to the t. I need that to equal 1 e to the t. So it must be that 3 alpha equals 1. So alpha is 1/3. So I now have a y particular. So my y particular is 1/3 e to the t. That is one particular solution to my differential equation. All right. Step 3, the general solution is just the sum of steps 1 and 2. Your general solution to the homogeneous equation plus the y particular that we just guessed. So y general, k e to the negative 2t, plus my y particular, which is 1/3 e to the t. So that process we used for guessing the particular solution, it's called undetermined coefficients because we guessed what form the solution had to have, but it had an undetermined coefficient, so we had to figure it out. In general, so this is important, this is how you guess what the form looks like. Ours was easy, right? It had to be e to the t. But in general, guessing the form of your particular solution, it's made up of a combination of the same type of functions contained in b of t and the derivatives of the functions contained in b of t. So sometimes you might guess wrong. When this happens, you just guess again, learning from your first try. So if your b of t, instead of being e to the t, if your b of t was sine t, right? Then your guess for y particular might have been alpha sine t plus beta cosine t, right? Because the derivative of sine is cosine. Okay. In this case, we only needed alpha e to the t because the derivative of e to t is still e to the t. So writing plus beta e to the t would have been redundant. All right, so we're going to take some time to work on these class activities. I'll save about half an hour for the demo portion of the next class.